I want to talk about the law of conservation of energy. In order to describe the law of conservation of energy, we're going to have to define what are conservative and non-conservative forces. So we've already defined work. We've defined the energy of an object to be its ability to do work. Okay? One of the reasons that the definition of energy is so useful is because in lots of situations, the total energy, remember the total energy is the kinetic energy plus all the flavors of potential energy. For many situations, the total energy is constant. Okay? That is a very powerful result. Okay? Let me show you how useful that could be. Okay? So suppose that you had a rock, and suppose that the rock was a height h. It was at a height h. Okay? And you wanted to know what was the speed. If you let go of the rock, what was the speed just before it hit the ground? Okay? So without the conservation of energy, the way that you would solve this problem is you'd say, okay, so it has an initial velocity of 0. I know what the acceleration is. It's due to gravity. I have my kinematic equations, and eventually you would arrive at the answer. Okay? Now that you may or may not be comfortable doing that, but here's another way you could do it. You could say, I happen to know that the total energy is not going to change in this problem. Okay? What is the total energy right before you drop it? So let's call that the initial total energy. Well, to answer that question, ask yourself what kind of energy does it have before you drop it? It's not moving, so it doesn't have kinetic energy. All it has is gravitational potential energy, so mgh. Now, right before it hits the ground, let's call that the final total energy. Okay, and let's think about what type of energy is going to be involved there. Well, it's lost all of its gravitational potential energy, so all it has is motion energy or kinetic energy, right? 1/2 mv squared. Now, even though both of those expressions involve different types of energy, they still have to be equal. Okay? So what that means is I could simply make an equation that implies that they're equal and solve for whatever I want. Okay, so let's solve for v. So cancel out the m's, multiply both sides by 2, and you see that v is the square root of 2gh. That's v final, if you will. Okay, so I can put a little f there if that helps. Okay, now I challenge you to, or invite you to work it out using the kinematic equations. You'll see that you get this exact same answer. Okay? One way to interpret what happened here was that instead of the quantity of energy changing, the type or flavor, whatever you want to call it, changed. We started out with pure potential energy and we finished with pure kinetic energy. This is something that happens all the time, where different types of energies change into other types. All right? In fact, there's a wonderful simulation that I would invite you to play with. It's called the PhET Energy Skate Park. And that has all kinds of wonderful things that help you understand these energy transformations. It's a guy on a skateboard on different sized tracks, different shaped tracks. And so as he moves, as his elevation, as his altitude, as his height changes, the potential energy and kinetic energy adjust in such a way to keep the total energy constant. Okay, for a lot of situations. There's a situation where it's not constant, which I'm going to address shortly. Okay, but that is a great that is a great thing to check out. Okay, so that was perhaps a slightly impressive result. Let me show you a much more impressive result. Suppose that you had a roller coaster and you wanted to calculate the speed at the very bottom. Let's say that it's a very fancy roller coaster. It's got all kinds of hills and turns. Okay, and then you have a cart at the very top, okay, with people, and so it's going to start out not moving at all, and it's going to slowly gain speed as it goes down the roller coaster track. Okay, and we want to know what is the final velocity at the very bottom. Okay, now to calc, and let's say it starts out at a height, let's give it a height h again. Okay, now to calculate this with forces, you would need to, what kind of forces are involved? We have gravity, we have the normal force from the roller coaster track. Okay, now the direction of the normal is going to keep changing because the direction of the roller coaster track is going to keep changing. Okay, gravity will be always straight down. Okay, and let's assume that the track is perfectly smooth. Let's assume that we don't have any friction or negligible friction. All right. So you could work out how the gravity, the different components parallel to the surface of the roller coaster track, work all that out, and you might, after a long time, be able to figure out the final speed. Now you would need to know the exact shape of the track, wouldn't you? Okay. However, you can avoid all that by simply using conservation of energy. Okay, the initial total energy was mgh, pure potential energy, gravitational potential. The final total energy was pure kinetic, just like the free fall example. So 1/2 mv squared. In fact, this is the same setup as we had for the free fall, isn't it? 1/2 mv final squared. So we're going to get the same exact answer. Okay, now that is weird. Okay. So indeed, it is the case that if an object slides down a ramp with, no matter what shape the inclined plane, the ramp, if it has hills, not hills, it'll turn out that you will end up having this, if it's frictionless, okay, that's a big if, then you'll have the same velocity at the bottom as you would if it was simply free fall. Okay? So that's a powerful example of the usefulness of the law of conservation of energy. We're making the much more general claim that the final velocity is independent of how you get down there to the bottom, how you get rid of your height, as long as it's frictionless. Okay? Big if. Now, so I haven't said when the total energy is constant. So that is what the law of conservation of energy gives us. So let me go ahead and state that now. All right, so, and I'll state it in my own way. Law of conservation of energy, okay? If a system of objects is only under the influence of conservative forces, then the total energy remains unchanged. or in other words, it's constant. Okay, that's the law of conservation of energy. So, in other words, as long as you have only conservative forces, then you're good to go. Total energy is going to be conserved. So the question then becomes, well, okay, so what are conservative forces? Well, there's lots of things that cause forces in the world. So I'm going to give you some examples of ones that are known to be conservative. Okay, and why are they called conservative forces? Well, they conserve energy. Okay, so examples of conservative forces. Okay, gravity is one. Spring forces. Okay, so anytime you have springs, you have conservative forces. Electrical forces. Okay. Those are the main ones that we will be focusing on in this class. Of course, as I said, there's lots of other forces, but basically, most of the forces that you encounter in this class will be conservative, with the exception of one annoying force. Okay? Examples of non-conservative forces. Okay? Well, maybe two examples, depending on your well, let me go ahead and just mention them. So, friction. Okay, friction is not a conservative force. And then you can also add air resistance, or you might argue that that's just another example of friction. Okay, so maybe you think that's only one. I only gave you one example of a non-conservative force. But the point is, if you rub against, like a carpet, non-conservative force. A ship sailing on the ocean and the wind is slowing down the ship, that's non-conservative force. All right? So there you have it. So a projectile moving through the air with air resistance, the total energy will not be constant. However, if the air resistance is negligible, approximately zero, then the total energy will be approximately constant. Okay? Now, let me finish with an example involving springs. Okay? So, suppose that we had something that's like a dart gun. Suppose I had a spring that was compressed. Okay, and I'm going to put a mass on the other end. And the spring has a constant, that spring constant K. Okay, and let's give it a value. Let's say K was 6 newtons per meter, and let's say this mass was 10 kilograms. Okay, so now we have to hold the mass, otherwise the compressed spring is going to push it away. Now, if we let go of the mass, the spring is going to push it to the right, and the question is, what's going to be the velocity after it loses contact with the spring? Okay, so again, initial total energy and final total energy are equal. So that's how we're going to solve for the final velocity. Okay, so the initial total energy, initially it's not moving, so we only have spring potential energy, 1/2 kx squared. And let's assume that it was compressed, let's say 5 centimeters. Okay? Now for the final total energy, it's going to be pure kinetic energy. Okay? And so setting those equal, we can solve for V or V final, whatever you want to call it. Okay? So let's do that now and see what happens. 1/2 kx squared equals 1/2 mv final squared. let's cancel out the 1/2. And V final, let's divide both sides by m. So V final squared is k over m x squared. So V final is the square root of k over m multiplied by x. So that's the square root of 6 over 10 times 5 centimeters, and let's convert that to meters, so 0.05. All right, and so, or if you like, the square root of 0.6 times 0.05. So go ahead and let's calculate that. I'll put that into my calculator as well. And I get, drum roll please, 0.038, so about 0.04 meters per second.